Number Sign Distributed Systems, Failure Patterns, Audio Learning Guide. Welcome to this deep dive into distributed systems failure patterns. Over the next 20 minutes or so, we're going to explore the critical concepts you need to understand when building reliable distributed systems. These aren't Azure-specific technologies. These are fundamental computer science principles that apply whether you're working with AWS, Google Cloud, on-premise infrastructure, or any distributed architecture. Let's start with a fundamental question. What makes distributed systems so challenging? The answer lies in the fact that when you have multiple services running on different machines, communicating over networks, you introduce failure modes that simply don't exist in monolithic applications. Networks can fail, services can crash, clocks can drift, and messages can get lost, duplicated, or arrive out of order. Everything we're going to discuss today stems from these realities. Staffier message delivery guarantees. Let's begin with message delivery guarantees because this is the foundation of understanding distributed communication. When one service sends a message to another service, whether that's through a queue, an event stream, or a direct API call, you need to understand what guarantees the system provides about that message actually arriving. There are three main categories of delivery guarantees, and understanding them is absolutely critical. The first is at most once delivery. This is the simplest model. You send a message, and maybe it arrives, maybe it doesn't. You fire it off and forget about it. There's no retry logic, no confirmation, no acknowledgement. The message might get lost in transit due to a network blip, and that's okay for your use case. You're guaranteed that the message will never be duplicated. It either arrives once or not at all, but you have no guarantee it will arrive at all. This pattern is appropriate for scenarios where losing occasional messages is acceptable, like telemetry data or analytics events. If you're tracking page views on a website and one view doesn't get recorded because of a network issue, that's probably fine. Your metrics will still be useful. The second guarantee is at least once delivery, and this is by far the most common pattern you'll encounter in production systems. With at least once, the system guarantees your message will definitely be delivered to the receiver, but it might be delivered multiple times. Why? Because the system uses retries to ensure delivery. If a network error occurs or the receiver is temporarily down, the message gets sent again. But here's the problem. What if the receiver actually processed the message the first time, but the acknowledgement got lost? The sender thinks it failed and retries, so now the receiver gets the same message twice. This is where idempotency becomes critical, and we'll talk about that in detail in just a moment. At least once delivery is the right choice for most business-critical operations, like payment processing, order fulfillment, or inventory updates. You absolutely cannot afford to lose these messages, so you're willing to deal with potential duplicates. The third guarantee is exactly once delivery, often called the holy grail of distributed systems. This means a message is delivered precisely one time. No duplicates, no losses. Sounds perfect, right? The problem is that exactly once delivery is extremely difficult to achieve in a truly distributed system. It often requires distributed transactions across multiple systems, which introduces significant complexity and performance overhead. In practice, what most systems do is fake exactly once semantics by combining at least once delivery with perfect idempotency and deduplication on the receiver side. If every duplicate can be safely ignored because the operation is idempotent, then from the business logic perspective, you've achieved exactly once processing, even though the message might have been delivered multiple times at the infrastructure level.
Validator idempotency, the key to reliability.
So let's dive deep into idempotency, because this is one of the most important concepts in distributed systems. An operation is idempotent if executing it multiple times produces the same result as executing it once. This property is what makes retry logic safe. Think about it this way. Imagine you have a bank account with $100 in it. If you execute the operation set balance to $150 10 times, what happens? The balance is $150. That's idempotent. But if you execute the operation add $50 to the balance 10 times, you've just added $500. That's not idempotent. And in a system with retriers, that's a disaster waiting to happen. Let me give you a concrete example. Imagine a user clicks a purchase button on your website. Their browser sends an HTTP post request to create an order. But there's a network hiccup, and the browser doesn't receive a response. From the user's perspective, nothing happened, so they click the button again. Now you have two requests. If your API isn't designed with idempotency in mind, you might charge the customer twice and create two orders. So how do you make operations idempotent? There are several strategies. The most common is to use idempotency keys. When a client makes a request, they generate a unique identifier, maybe a UUID, and include it with the request. The server stores this key along with the result of the operation. When a duplicate request comes in with the same key, the server recognizes it's a duplicate and returns the cached result instead of processing it again. Stripe's Payment API is a great example of this pattern in action. Every payment request includes an idempotency key, so if your retry logic kicks in, you won't accidentally charge a customer twice. Another approach is to leverage natural idempotency in your operations. HTTPPUT requests, for example, are naturally idempotent because they specify the entire desired state. If you put a resource with specific values, doing it 10 times gives you the same result as doing it once. Post requests, on the other hand, typically create new resources, so they're not naturally idempotent unless you add that behavior explicitly. Database constraints can also enforce idempotency. If you have a unique index on an order ID, attempting to insert the same order twice will fail on the second attempt. That's a form of idempotency enforcement at the data layer. The key insight is this. In a distributed system with retries, which is basically every distributed system, you must design for idempotency. It's not optional. It's a fundamental requirement for correctness. Frakreutzer, retry strategies and resilience. Now that we understand idempotency, let's talk about retry strategies, because retries are how we handle transient failures in distributed systems. A transient failure is a temporary problem. Maybe a service is briefly overloaded, or there's a momentary network issue. These failures often resolve themselves if you just try again. The naive approach to retriers is to just try again immediately. Request failed, try again. Failed again, try again. But this creates several problems. First, if a service is already struggling under load, hammering it with immediate retries makes the problem worse. Second, if many clients all retry at the same time, you create what's called a thundering herd problem, where a wave of retries overwhelms the system. The solution is exponential back-off. With exponential back-off, you increase the delay between retry attempts exponentially. Your first retry might happen after 1 second, then 2 seconds, then 4 seconds, then 8 seconds, and so on. This gives the struggling service time to recover and prevents you from making the problem worse. But exponential back-off alone isn't enough. Imagine you have 1,000 clients all making requests to a service at the same time. The service goes down, they all fail and schedule their first retry for 1 second later. 1 second passes and boom, 1,000 simultaneous retry attempts hit the recovering service. Even though you used exponential back-off, you still have a thundering herd problem because all the clients were synchronized. The solution is to add jitter, randomness. Instead of retrying after exactly 2 seconds, you retry after 2 seconds plus or minus some random amount. Maybe 1.7 seconds, maybe 2.3 seconds. This spreads the retry attempts over time and prevents synchronized waves of traffic. Another critical pattern is the circuit breaker. Imagine you have service A calling service B, and service B is completely down, not temporarily struggling, but fully offline. Without a circuit breaker, service A will waste time and resources making requests that are guaranteed to fail, waiting for timeouts, and retrying. With a circuit breaker, after a certain number of consecutive failures, you stop even trying to call service B for a cooldown period. You open the circuit and fail fast instead. This prevents cascading failures where service A gets backed up waiting for service B, and then service C gets backed up waiting for service A, and your entire system grinds to a halt. After the cooldown period, the circuit breaker transitions to a half-open state, where it allows a small number of test requests through. If those succeed, great, service B has recovered, and we close the circuit and resume normal operation. If they fail, we open the circuit again and wait longer. These patterns, exponential backoff, jitter, and circuit breakers, are your primary tools for building resilient distributed systems that can handle failures gracefully. Poison messages and dead letter queues. Let's talk about a specific failure mode that comes up constantly in message-based systems: poison messages. A poison message is a message that, for whatever reason, cannot be successfully processed by the consumer. Maybe it's malformed. Maybe it triggers a bug in your code. Maybe it references data that doesn't exist. Or whatever the reason, every attempt to process this message fails. Here's the problem. Most message queue systems implement at least once delivery with automatic retries. So when your consumer fails to process a poison message, the queue automatically redelivers it. Your consumer tries again and fails again. The queue redelivers it again. You've created an infinite loop, and this one bad message is blocking your entire queue from processing any other messages. The solution is to implement a maximum retry count and use a dead letter queue. The idea is simple. Try to process a message, say, 5 times. If it fails all 5 times, instead of retrying forever, move it to a special dead letter queue, a separate queue for messages that couldn't be processed. This accomplishes several things. First, it unblocks your main queue so other messages can be processed. Second, it preserves the problematic message so you can investigate what went wrong. Third, it gives you visibility into these failures through monitoring and alerting. In production systems, you should absolutely be monitoring the depth of your dead letter queues. If messages are piling up there, something is wrong and needs investigation. Maybe there's a bug in your code. Maybe there's a data quality issue. Maybe a downstream dependency is unavailable. Whatever it is, the dead letter queue is telling you there's a problem that needs human attention. Some organizations have processes for replaying messages from the dead letter queue after fixing the underlying issue. Others treat them as a source of truth for investigating failures. The key is that you're failing gracefully and maintaining visibility rather than letting poison messages bring down your system. The saga pattern for distributed transactions. Now, let's tackle one of the most challenging problems in distributed systems. How do you handle transactions that span multiple services? In a monolithic application with a single database, this is straightforward. You use database transactions. You start a transaction, make all your changes, and either commit them all together or roll them all back together. The database guarantees atomicity. But in a microservices architecture, you might have an order service with its own database, a payment service with its own database, and an inventory service with its own database. How do you ensure that creating an order, charging a payment, and reserving inventory either all succeed or all fail together? The traditional approach would be a distributed transaction using something like two-phase commit. But distributed transactions are complex, slow, and fragile. They require locks across multiple systems, which hurts performance and availability. They don't work well across organizational boundaries. Good luck getting your payment processor to participate in your distributed transaction. The modern approach is the saga pattern. Instead of trying to make all the changes atomically, you make them sequentially. And for each step, you define a compensating transaction that undoes it if something goes wrong later. Here's how it works. Imagine processing an order. Step 1. Create the order in the order service. Step 2. Charge the customer's credit card in the payment service. Step 3. Reserve the items in the inventory service. If Step 3 fails, maybe the items are out of stock, you don't try to roll back a distributed transaction. Instead, you execute compensating transactions, refund the credit card charge, cancel the order. You're undoing the previous steps with new operations, not trying to roll back database transactions. There are two main flavors of sagas. In choreography-based sagas, services communicate through events. The order service creates an order and emits an order-created event. The payment service listens for this event, charges the card, and emits a payment-processed event. The inventory service listens for that event, reserves items, and emits an inventory-reserved event. If any step fails, it emits a failure event, and other services react by executing their compensating transactions. In orchestration-based sagas, you have a central coordinator, an orchestrator function, perhaps using something like Azure Durable Functions or AWS Step Functions, that explicitly calls each service in sequence and handles the compensation logic if something fails. This gives you better visibility and control, but introduces a central component that could become a bottleneck or single point of failure. The saga pattern requires careful design. You need to think about compensating transactions for every operation. Not all operations can be easily undone. You need to handle partial failures, where maybe the compensation fails too. But it's the pragmatic solution for distributed transactions in modern architectures.
Eventual consistency and the CAP theorem.
Let's talk about consistency models, because this is where a lot of confusion happens. In a distributed system, you're constantly making trade-offs, and the CAP theorem formalizes one of the most important trade-offs. CAP stands for consistency, availability, and partition tolerance. The theorem states that in the presence of a network partition, when parts of your system can't communicate with each other, you can only guarantee two of these three properties. Consistency means every read receives the most recent write. Availability means every request receives a response. Partition tolerance means the system continues to operate despite network failures. In practice, partition tolerance isn't optional. Networks fail. So you're really choosing between consistency and availability. Do you want a system that always returns the most up-to-date data but might be unavailable during network issues? Or do you want a system that's always available but might return stale data? Many modern systems choose availability and embrace eventual consistency. With eventual consistency, if you stop making updates to the system, eventually all replicas will converge to the same value, but at any given moment, different replicas might have different values. This is okay for many use cases. If you're reading your social media feed and you see a slightly stale like count, that's probably acceptable. The system is available and responsive, even if the data isn't perfectly consistent at every millisecond. The challenge with eventual consistency is handling conflicts. If two users update the same data at the same time in different locations, which write wins? Common strategies include last write wins, where you use timestamps to determine which update is newer, or more sophisticated approaches like vector clocks and conflict-free replicated data types that allow the system to merge conflicting updates intelligently. The key is to understand the trade-offs and choose the consistency model that's appropriate for your use case. Financial transactions probably need strong consistency. Social media likes can tolerate eventual consistency. Shopping cart contents might be somewhere in between. Observability in distributed systems. Finally, let's talk about observability, because when things go wrong in a distributed system, and they will, you need to be able to understand what happened. In a monolithic application, you can set a breakpoint and step through the code. In a distributed system with dozens of services, that's not possible. You need different tools. The foundation of observability in distributed systems is correlation IDs. Every request that enters your system should be assigned a unique identifier. And this identifier should be propagated through every service call, every log statement, every database query. When you're investigating an issue, you can search your logs for this correlation ID and see the entire path the request took through your system. Distributed tracing takes this further. Tools like OpenTelemetry, Jaeger, and Zipkin allow you to visualize the request path as a trace with spans representing each operation. You can see that a user request came in, which called service A, which called services B and C in parallel, which each called service D, and you can see the latency of each operation. This makes it possible to understand complex interactions and identify bottlenecks. You also need structured logging. Don't just log text strings, log structured data, JSON objects with fields, so you can query and aggregate logs effectively. When every service logs with consistent field names and includes the correlation ID, you can answer questions like, "Show me all errors for this customer in the last hour," across your entire distributed system.
Conclusion.
We've covered a lot of ground here: message delivery guarantees and the importance of idempotency, retry strategies with exponential backoff and jitter, circuit breakers to prevent cascading failures, poison messages and dead letter queues, the saga pattern for distributed transactions, eventual consistency and the CAP theorem, and observability through correlation IDs and distributed tracing. These aren't Azure concepts or AWS concepts. These are fundamental distributed systems patterns that you'll encounter regardless of what technology stack you're using. Understanding these patterns deeply will make you a better engineer and prepare you to build robust, reliable distributed systems. The key takeaway is this: distributed systems fail in ways that single machine systems don't. Embrace failure as a normal operating condition, design for it. Build in retries, idempotency, and graceful degradation. Monitor everything and understand the trade-offs you're making between consistency, availability, and partition tolerance.